Okay, so I've got 10 minutes. I'll get through this as quickly as I can. This is going to be about using convolutional neural networks for post-processing of reconstructed images, and you'll see why that's useful in a moment. So starting off with a very simple building block of convolutional neural networks, they use convolution. So what we're going to use a lot in these diagrams, in these few slides, is this kind of notation here. We've got, for example, an image, for example, a vector X, and we're going to represent that as like a kind of a column vector like this, some kind of rectangle. And what we're often going to be doing is running that through a convolution operator, such as this one here. And we'll denote the size of the convolution kernel here, for example, is if it's 3D, it would be 5 by 5 by 5. This is just a 2D image though. And I'm just showing a visualization of an example kernel here. This would just be the identity kernel, just the Dirac delta function, if you like, a Kronecker delta, which, if it's just a delta, will give you a mapping from input to output that is the identity. And here there's no activation. Now, so with convolutional neural networks, we can do a convolution with a kernel, and then we can also do an offset or a bias, and then a nonlinear activation, such as a ReLU function, which sets negatives to 0, for example. And that's where we get the nonlinearities in our mappings, which is what can make them quite powerful. But just motivating things here with a simple example of just an architecture consisting of just one 5 by 5, it's 2D, not 3D, convolution kernel. And in which case we'd just be seeking to learn a 5 by 5 kernel, which is 25 parameters, which will map a noisy input to a high quality reference. Now here, it's just the identity, so I'm not doing anything. But if I use training data, and this is the whole point of supervised learning as used in machine learning, deep learning, what we've got is an example of what we need to happen with this operator. So the input is a noisy image X, and the target would ideally be a high quality reference or ground truth. This is simulated data, so we have the ground truth. And what we do is say, well, okay, if that's my input, I want the output to look like this target here, and I'll use a loss function. That's machine learning talk for an objective function. I hear Jan LeCun prefers now to say objective function sometimes, so it's like machine learning people are learning from reconstruction people. Anyway, the objective function or loss function here is just a mean square error, where we're saying, therefore, find the parameters for a kernel such that the output, when you put this noisy image into this convolution, such that the output y, so I'm showing the values here, need those to agree with the high quality target t by a mean square error loss function or objective function. And normally it's backpropagation or whatever your favorite optimization algorithm is to do this kind of optimization. So I think this one was done with just a simple grid search. But the point is the least squares methods we've been looking at, gradient descent and so on. In fact, stochastic gradient descent are often very much used in machine learning. So this is just the core motivation for a building block which for convolutional neural networks. This one, let me just show you what it does. Once we've trained it up, instead of the identity kernel, what we get is a smoothing kernel. So this has been machine learned, if you like, based on trying to get that to match that. And so this is the best we can do with one single kernel, just to smooth it an optimal amount according to the noise in the image. And that's just a depiction of what the convolution process is doing. We don't have time to go into that in more detail. If we had a blurred input, we could learn a kernel that could sharpen it up, and now we get negatives in the kernel. Just showing again that one single kernel can actually do quite a bit. So now to take that concept of learning convolution kernels to get an input to match a desired target, as in supervised learning, I'll build this up one step further for mapping low count data to higher count data, as this is a post-reconstructed PED image, MLEM reconstruction. Again, we're depicting that as this kind of rectangle here. Now we're going to run it through a convolutional layer. It's called that now because really we're going to not just have one kernel here, but 32 kernels. So what we're going to do is learn all kinds of different operations that do all kinds of possibly very interesting things related to our endpoint task. So here I'm showing 32, so imagine 32 of those kind of images. These are called feature maps, 32 feature maps obtained by convolving that input with 32 different learned kernels. Now here also we've got a nonlinearity. This is a sigmoid. That's again, it just forces values between 0 and 1. The network you'll be working on later uses a prelude. We'll touch on that briefly. But anyway, a bias and an activation will give some interesting outputs here that are just convolutions, offset, and activations, feature maps. And then what we can do is process those again, because often these will be quite interesting, but still not close enough to where we're going. This is going to be mapping this low count, you'll see it in a moment, to a high count image. So what we do is we learn more parameters. And so here now we've got another convolutional layer composed of 32 kernels. These ones are smaller kernels, and they're also going to need to be 32 channel kernels. So one feature map output here is going to correspond to using a 3x3x3 kernel operating on each and every one of the input feature maps. So there needs to be 32 channels of each kernel. And because we've got 32 kernels, therefore we actually have 32 feature maps. So here we're learning 32 channel 3x3x3 kernels. So you can see how the complexity can build up quite nicely here to do some interesting mappings. And again, there will be a bias and an activation, so these become non-linear as well. And then finally, we can glue together those feature maps with a 1x1x1 convolution. That's, convolving with a delta function just gives you the same thing, but just scaled. But again, this is going to now need to be 32 channels to glue together these 32 feature maps with different weighting factors, and then an exponential linear unit for the nonlinearity, glue them all together to finally arrive at a single image output, a prediction. And so you can see here, what we've got is a whole cascade of convolutions, nonlinearities that we're seeking to learn in order to go from example pairs of low dose, high dose images. And we just want to find the parameters that are going to achieve that overall nonlinear mapping. And this is now already ramping up to between 20 to 40,000 parameters that are being learned in all of these multi-channel convolutions. Also in this work, this is the work that Casper did sometime, or last year, published now. Also, we used an MR image as the input here. So this is the MR and the PET as two input feature maps, if you like, to this series of convolutional layers. Training data was very limited in this case, only 2 to 3 training pairs, mapping low count to high count images. And again, we used the mean square error loss function. And the optimizer was a modification, a kind of a more hybrid version of stochastic gradient descent. I haven't got time to go into that in detail. And a very small learning rate, so very small updates of the parameters edging towards the minimum of that mean square error loss function. And obviously, you need to use validation data during your training as well to decide when to stop the training process. Okay, now getting on to the final few slides to introduce the network that you'll be working with Gail. This is his very nice paper published earlier on this year in Neuroimage, where what he did was the idea of mapping inputs to outputs, where now the goal is not just, for example, to go to higher count images, but actually to rapidly predict what a MapEM reconstruction would look like. So he just takes the standard vanilla OSEM reconstruction, takes hopefully a perfectly registered T1 weighted MR for that PET as well. Those are now the two inputs, and the desired output of the convolutional neural network is to predict what would the long several hours to calculate MapEM Bauscher guided reconstruction look like. So it's basically accelerated MapEM reconstruction and also higher count mapping at the same time. So first of all, we've done a convolutional layer here and here to pre-process the MR and the PET. So we've got 15 feature maps for each of those. Those two get concatenated to give 30 feature maps to go into another convolutional layer, and so on and so on and so on, all the way up to the gluing together layer at the end. And here he's been using parametric ReLU. Basically, that's like a kind of a leaky version of the ReLU, where you don't just set negatives to 0, you just massively attenuate them, and you learn the parameter of to what level you scale down the negative values. But that, again, importantly introduces a non-linearity into the network. So what we end up with here overall is a non-linear shift invariant mapping, where they trained it up quite impressively on, I think, about 26 patient data sets. Gail will be able to give you all the details. They used data from 2 different scanners. I think it's from the GE Signet as well as the MMR, 2 different tracers, and they used lots of patches, lots of augmentations of the data, again, beyond the time I've got today to go into in detail, to train up all of those convolutional layers, about 170,000 parameters, using mean square error loss and the Adam optimizer. And importantly also to note, what they do is learn not how to map from that to that directly, but they learn the residual image. In other words, learn what is the thing that you need to add on to the OFCM image to get to the anatomically guided reconstruction. So obviously it's massively faster, maybe a second on GPU compared to proper MapEM reconstruction from first principles. And also impressively, they demonstrated it out of domain on a different tracer. This is F18 FET for neuro-oncology, where you've clearly got an abnormality here. And this tracer was not used in their training sets. That's very nice. Here's the corresponding MR. They put this into their pre-trained network that had used 2 scanners, 2 different tracers, I think 26 patients. And they get a nice MapEM prediction that looks like this. When compared to the actual one, you can see they're doing very well indeed. If you start scrutinizing, you can see a few differences, but I'm sure we can forgive that. And so that really is me done in 11 minutes to just summarize an introduction to Georg's very nice CNN for PET imaging. Thanks.